Today we're going to do chapter 6.3 on position vectors. Okay, so basically when we have position vectors, we're dealing with a position. Okay, and what position is this, right? It's usually the point O, which is the origin. So if you look at page 187 of your textbook, right, we will be talking about position vectors today. So now I'll give you the example on page 187. Okay, we talk about the point P down here. Okay, the point P is denoted by OP. So what is this O? The O is the origin. So if you notice here, OP is actually just like we have done the column vectors already. It will be 2 and 3. Hence OP is 2, 3, but is with reference to the point O. Okay, so now if you look at the diagram on page 187, all right, we have this point with this vector PQ here. So as you know, PQ, this is a vector here, PQ can also be rewritten as PO plus OQ. So PO plus OQ. If you notice, OP with respect P with respect to O, the OP is a vector P, while OQ is the vector Q itself. So if OP is equals to the vector P, what is PO? PO will be equals to negative P. Hence, in this case, if PQ is equals to PO plus OQ, hence PQ is equals to negative P plus Q. So if I rearrange that, it is Q minus P. Okay, so notice this. So if we are looking about PQ, all right, you notice that first Q comes first, okay, and then P comes second. So with respect to position vectors, how I like to think of it is always the second letter minus the first letter. Okay, let me just give you another example, okay, just below there. So like for example, AB in this case, right? So if the vector OA is equals to A and the vector OB is equals to B. So what happens here is this: if I'm looking at the vector AB, okay, as I said earlier, the second minus the first, the second letter is B minus the first is A. Hence, in this case, AB can simply be vector B minus vector A. And this can also be seen in another way. If AB is B minus A, what do you think is the vector BA? Okay, same thing, it will be the second letter, which is OA minus OB. So what I get is A minus B. Okay, once again, if you notice, the second minus the first when we come to position vectors. Okay, never mind. We shall now look at page 190, try 20, for a better understanding of how position vectors work. Okay, so first and foremost, there's OA, OB, OC, and OD. These are all expressed as position vectors. So like OA is equals to the vector A, then OB is equals to the vector B, OC is equals to the vector C, and OD is equals to the vector D. So simply AD, again with position vectors, it will be second, which is OD minus OA. So in this case, what we get is D minus A. Similarly for BC, BC is OC minus OB. So what we have here is the vector C minus the vector B. Okay, now for part B, okay, part B we have to show that the vector D equals to A minus 2B plus 2C. Okay, if I'm not, I'll just take some time here. I just shrink this so that I have more space to work with. Okay, so for part B. Okay, first, this case, they don't really give you very much clues there, all right? But if you notice, there's a piece of information we haven't quite used yet, which is AD equals to 2BC. So maybe we just start with that first. So first I'll say this, AD is equals to 2 times of BC. So what is AD? If you notice in the earlier part, in part A, I know that AD is D minus A. Similarly, BC, as we found in our earlier part A, okay, is equals to vector C minus B. So what happens here is this, D minus A equals to 2C minus 2B. So just like we do a bit of manipulation there. So if here is negative A, you plus vector A on both sides, it becomes positive A on the right hand side. So what I get here is A plus 2C minus 2B. I just rearrange the entire equation around, is A minus 2B plus 2C. And that is what we have want to show in part B. So down here, just go on and write the word here, shown. Still on page 190, we are at try it 21. So they say find OE in terms of C. So what we can do is this. Notice that we have a piece of information here, which is C over ED equals to 4:3. Okay, so now if you look at the diagram, what we have, CE is to ED 4:3. So in total, actually I can say that this whole thing, if this CE is 4 units, ED is 3 units, in total this will be 7 units. So I can write this down. I will say that CE is equals to 4/7 of CD. So I can say that CE is 4/7 of D minus C. Second letter minus away the first letter. Now I want to find OE. So what is OE? OE is simply equals to OC plus CE. Okay, so OC is the letter C. CE is 4/7 of D minus C. If I just open up expand the brackets, open up and simplify, what I find I get is 3/7 of C plus 4/7 of D. And now I've already found OE in terms of C and D. Okay, I'm just going to move on to exercise 6.3, alright, to give you a bit more examples about position vectors. And this can be found on page 194 of your Discovering Mathematics textbook. Okay, so now what we want is the position vectors of A, B, and M as column vectors. This is actually quite simple. So what in essence the question wants from us is this. So the position vector of A will be OA. So I can just write it down as -6 minus -3. Similarly, alright, what we have is OB. Okay, the coordinates of B is 4, 5. Hence the position vector OB is 4 and 5. Okay, now if I am trying to find the position vector of M, okay, such that AB equals to 2AM. So now, in order for me to find the column vector or the position vector of M, the piece of information that I need will come from here. AB equals to 2AM. So I'll just go right ahead and write it down. AB is equals to 2 times of AM. Okay, when it comes to position vectors, I always find it a bit easier to first manipulate the equation. So AB, alright, will be OB minus OA equals to 2 times, if AM expressed as position vectors would be OM minus OA. Then what we get is OB minus OA equals to 2 times of OM minus 2 times of OA. Okay, what am I going to do right here is this. I'm just going to put this guy on the left hand side. Then I'm going to put this guy on the right hand side. Okay, let me shift this whole thing around. Then what I'll get here is 2 OM is equals to OB plus 2 OA minus OA plus OA. Alright, then after that I want to get OM. Okay, how do I get rid of 2? Just like the 2 over here is just like algebra. So if I divide by 2 on both sides, I get half of OB plus OA. So it's half of OB plus OA. So I just do a bit of quick mental calculation here. OB plus OA. 4 plus negative 6 will give me negative 2. And similarly, OB plus OA, 5 plus negative 3 will give me 2. So what I get is half times negative 2 is negative 1. Half times 2 is 1. So my OM value is negative 1 and 1. So I've done part A already. I found OA, I found OB, and after this lengthy portion here, I've also found the value of OM. Okay, lastly, in part B, I think the hard part of this question is over. What they want for us is to find the magnitude of the position vector M. So what essentially they want us is to find the magnitude of OM. So the data I can get from here. So the magnitude here is negative 1 square plus 1 square square root. The magnitude of OM in this case is 1.41 units. Okay, now we are on page 194 of your textbook, and I am going to look at question 3. Okay, A1. Okay, since we are dealing with position vectors, AB, as we recall, is the second letter OB minus the first letter OA. So AB is simply B minus A. Similarly, alright, for BC, second letter is OC minus the first letter, which is OB. So what I get is C minus B. Similarly, for CA, second letter minus first letter is OA minus OC, which gives me vector A minus C. Okay, very chop. Then we do part B, AB plus BC plus CA. So AB plus BC plus CA. AB is B minus A. Okay, plus BC is the vector C minus vector B, plus CA is A minus C. So if you simplify all of that, you notice that it gives you a 0 vector. And that makes perfect sense as well, because if you look back at the diagram there, okay, so I'm doing this, AB plus BC plus CA, you end up at the same point again, so therefore it becomes a 0 vector. Okay, I'm now going to do question 4, alright, on page 195. So for this, I'm going to do A, part 1, R minus P. Okay, since we are dealing with position vectors would be second second letter minus the first letter. So R is the second letter, P is the first letter. Okay, so it's second minus the first. So I can state the vector as PR. okay, because if not, right, okay, it will be second letter, which is OR minus OP, which is R minus P. So we're actually working in reverse here. So similarly, okay, S minus Q, second minus the first. So what we are looking for is actually QS. So if I just write down, the vector here is QS. Okay, so now I move on to part B. What is the relationship between the magnitude of R minus P and S minus Q? Okay, so if I just take a look here at the diagram, R minus P is PR. Okay, so PR is like this. And then I use another color for QS. Okay, QS is like this. So notice that both of them are the diagonals of the rectangle. So what is the same about these two diagonals? Okay, they will have the same magnitude, the same length, so to speak. So therefore, the statement I can make here will be this. I will say that PR is equals to QS because they are the diagonals of rectangle. So, and we know that the diagonals of rectangle will have the same magnitude. So therefore I can conclude that the magnitude of R minus P is equals to the magnitude of S minus Q. Okay, which brings us to the very last question of 6.3 position vectors before you can go and try out some questions on your own. Okay, so now A part 1. AT. Okay, so for position vectors, AT, alright, in this case is 2/3 of AB. How did I write that down? This piece of information came from here. Okay, then what we know is this. AB will simply be the second letter minus the first letter. Hence, it is OB minus OA. So I can write it down as 2/3 of B minus A. So if you expand the brackets, which is 2/3 B minus 2/3 of A. Then we move on to A part 2. A part 2 wants us to find OT. In this case, what we can do here is to start with this, where we have AT is equals to 2/3 B minus 2/3 A. Now, AT, if I re-express it, it can be OT minus OA equals to 2/3 B minus 2/3 of A. I will carry on my working down here. So what I get is OT is equals to 2/3 B minus 2/3 A. So it will be plus OA down here. But what I'm going to do here is this. I will just rewrite OA as plus A. So OT, vector OT is 2/3 B plus 1/3 of A. Okay, so there's part 2. Then finally okay, for down here I'm just going to, okay, I'll just leave it first. For A part 3, OC. Okay, OC in this case, alright, if we look at the diagram here, OC is down here. OC can be written as OA plus AC. Okay, and AC I know is equals to 3 times of OB. So I'll use all these pieces of information to solve for OC is equals to OA plus AC. OA is simply A, and AC I know is 3 times of OB. So 3 times of OB gives me 3B. Hence OC is A plus 3B. Now they ask, what can you deduce about OT and C? Okay, so now OT and C will be related to OT and OC. So if I were to do this, okay, if I look at OT, okay, we are doing part B now. Okay, OT is 2/3 B plus 1/3 of A. So if I were to factorize 1/3, what I get is 2B plus A. Okay, alright, what I get is A plus 2B. Okay, now usually we are looking out for parallel vectors, but if you notice in this case, OC is A plus 3B, OT is 2B plus A. Alright, yeah, let me just rearrange to show you that they are actually different. Is A plus 2B. So for OC, what I have, alright, is A plus 3B. For OT, I get A plus 2B. So in this case, OC is not K times of OT. It's not. Okay, so OC, okay, is not K times of OT. Okay, so to put it down in words, I'm going to say this. OT and OC are not scalar multiples of each other. Okay, therefore, OT and OC are not parallel. And therefore, if they're not parallel, okay, it means that OT and C do not lie on the same straight line. Right, now we go on to part C. Alright, so part C, I know that we are trying to find the area of OBT to area of OAB. So first and foremost, can you identify what actually links the triangle OBT to OAB? Are they similar triangles? Well, in this case, I don't think so. What they are actually triangles with the same height. So if you can't see it, just let me help you there. Okay, over here and over here, okay, they will share the common height h over here. Okay, so now I also know this piece of information earlier, whereby okay, AT is 2/3 of AB. So basically over here, let me put it down in green. This is 2 units, this is 1 unit. Alright, because they say here that AT is 2/3 of AB. So now with the information that they are triangles with the same height, and also okay with the ratio 2:1, so area of OBT, so area of OBT, let me just write it down. Area of OBT, half times base, okay, in this case that 1 unit, okay, times the common height h over area of OAB is it'll be 2 plus 1, so it gives me 3 units. Okay, because where do I get the 3 units from? Over here. Okay, times the common height h. So if you notice, what can I eliminate? The half and the h. So what I'm left with here is equals to 1 out of 3. And that brings us to the end of 6.3 position vectors. So do practice what